Okay, these are the notes for Unit 4, Day 10, and we start on page 28 of your note packet. And we are going to look at something called L'Hôpital's. And just a quick grammar discussion here. L'Hôpital's is it can be spelled like this. You can put an S here next to the O, so it looks like hospital. There's two correct spellings, and but definitely pronounce L'Hôpital's. Don't pronounce it La Hospitals. It's not the appropriate pronunciation. So it's L'Hôpital's rule for determining limits of indeterminate forms. Okay, so and so the essential question is when are we allowed to apply L'Hôpital's rule for calculating limits? Okay, and the answer is kind of in the title, right? We can apply it when we have an indeterminate form. So so we're back to talking about limits. And I kind of said that we were moving away from limits after Unit 1. I kind of lied. Sorry about that. But I think you're going to really love L'Hôpital's. It makes calculating indeterminate forms super duper easy. So we're gonna love this. I guarantee it. Okay. So just keep an open mind, right? The only limits that exist are the ones in your mind. So don't do that. We're gonna like this a lot. Okay. Anyway, back to this, right? This is our flow chart. And so we're up here with our function, we're being asked to evaluate a limit. And the first thing we do is plug in that value A, right? And we plug in the value A, and then we're at a crossroads, right? We say, hey, we get this value f of A. And if it's numeric, if it's finite, super, we got the limit. Done, right? Like the limit of x squared, this parabola as we approach 3 is 9, right? It's the function value. We know that this makes a nice U-shaped thing. Okay, well, that's the first crossroads we could go down, or we could go down here and say, whoa, wait a minute, I got 0 in the denominator. And we're like, well, that's still okay. That just means I have an asymptote, a vertical one, right? And then I just got to look on either side to see if I'm going up to positive infinity or down to negative infinity, right? And that wasn't so bad either. And then we got to this third crossroads and we're like, whoa, what happened here, right? We get 0 over 0, and that does not fit the asymptote thing. That gets us, we don't know what that gets us. We argued this, right? We said, wow, is that 0? Is that 1? Is that undefined? What is that? And the fact that we could argue that meant that we had something that was indeterminate, right? We were looking at that going, we could argue that all day long based on how you want to evaluate 0 over 0. So it's indeterminate. We don't know how to evaluate that. And then that led us down, right, to the middle part of the flow chart. And then just a caveat, infinity over infinity, we can have the same argument with, right? That led us down to this middle part of the flow chart where we had to either factor or use conjugates or use trig identities, and we got really super frustrated sometimes. So we can bypass all of this. This is why I think you're going to really like it. So remember, the factoring was like, hey, I've got these quadratics. I'm going to do the star method and factor them, and then I'm going to have these canceling factors. And these canceling factors are where this makes it 0, right? This is the 0 over 0 part. And we get, so if we can cancel that, we get rid of the 0 over 0 part. We get rid of the indeterminate part. And then we have something we can actually evaluate. And that wasn't so bad. The conjugates were a little trickier, right? But they were still, and they proved to be a little problematic. But it was just meant there was more algebra. And then the trig identities really caused some temper tantrums because I don't know of anybody who's a huge fan of trig, maybe me, but I'm just that kind of person. So the cool thing is, like I said, we can bypass all of this, and we are going to come over here, and we are going to use L'Hôpital's. And this is the criteria, right? It has to be indeterminate. Okay. And so if we can use that and bypass that, that just means we use L'Hôpital's, we come back here and we evaluate it. Okay, just like we would here, right? We would use factoring and we would evaluate, we plug back in. And so this is what L'Hopital's does for us. This is kind of cool. Okay, so we have this rational expression here, right? And this is, let's just go back. It's okay, it's a different quadratic. I wasn't sure about the same or a different quadratic. Okay, I guess it's a different quadratic. We're going to have to factor one more time. Okay, so we're going to check the status here, right? We're going to say, let's take the limit as x approaches 5. And we're going to plug 5 in. And we're going to do this math. 25 minus 10 minus 15. 25 minus 15 minus 10. Guess what? We got 0 over 0. So we know we have an indeterminate form. So that's the first step. First step is we really have to check the status, right? We have to verify that it's indeterminate. And we had to do that even using the other methods, right? If we were going to factor or use conjugates or use trig, we were going to have to check that status as well. So that's nothing new. Okay, let's do the old way, right? Let's factor that. So we get x minus 5, x plus 3, and x minus 5, and x plus 2. So the x minus 5s cancel, right? This is what at 5, this gives us 0 over 0. This is our indeterminate condition, so to speak. And we also know that created the hole in the graph, right? That's how we got this, right? This asymptote is here because this x plus 2 factor in the denominator is still there, right? So we know we have an asymptote at -2, but we don't really care because we are focused on when x is equal to 5. We're focused on this part of the graph, and we don't care what's happening over here. Okay, so we can simplify this. We can plug in a 5, and we get 8 over 7. So we know that if you can see 8 over 7, just a little bit bigger than 1, that's the limit, right? Limit is it gives us that language. We can find the y value as x approaches a certain location, right? Well, L'Hopital says this. This is like the bee's knees. I just love this. Okay, L'Hopital says this. We take the limit as x approaches 5 of a function, and that function is rational, like we have up there. We can literally differentiate the top. Look at this, 2x minus 2, right? If we look at the top all by itself, the derivative of the top is 2x minus 2. And we can differentiate the bottom. So again, look at the bottom here, right? Take the derivative, it's 2x minus 3. And this limit does exactly the same thing as the original question. So in red here is the rational expression 2x minus 2 over 2x minus 3. Okay, you can see that the denominator has an asymptote at 1.5, right? 2 times 1.5 is 3, and 3 minus 3 is 0. But this is the cool thing, that this, we don't care what it does over here, because all we care about is where x is approaching 5. This derivative does the exact same thing as the function does, but the hole is gone. So remember that hole in the graph right here is from the original expression. It passes right through that hole. In other words, this x minus 5 factor has been removed. And so if that x minus 5 factor has been removed, then this is no longer indeterminate at 5. And we can plug 5 in. 2 times 5 is 10, minus 2 is 8. 2 times 5 minus 3 is 7. And we can find the limit that way. No more factoring, no more conjugates, no more trig identities. We can use derivatives to now address all of those limit questions. And that whole center part of the flowchart goes away. So you might ask me, you might ask yourself, well, why didn't you tell me that at the beginning of the year, right? This is so much easier. Well, think about it. Could we have done this in September? The answer is no. Why couldn't we have done this in September? Because we did not know how to differentiate. We did not know what a derivative was. We had to rely on algebra and trig, okay? now that we have a little bit of knowledge about derivatives, we can use that power and go back to limits and handle our indeterminate forms that way. Makes it much easier. Okay, so here's the procedure, right? We check the status. We have to verify, and the grader needs to see that you verified that it is indeterminate. Okay, so you check the status, you get your 0 over 0, or you get your infinity over infinity. Okay, and you say indeterminate. That's all you have to do. 0 over 0, indeterminate, or infinity over infinity, indeterminate. Okay, and then you can go ahead and differentiate the top and differentiate the bottom. Now, I want to caution you. This is not the quotient rule, right? The quotient rule is low d high minus high d low over low squared. We're not doing that. Okay, we are taking the derivative of the top like it's its own little thing, and the derivative of the bottom like it's its own little thing, and we're keeping that ratio. Okay, because we know that behaves the same. I'm going to go back to the previous screen. We know the derivative, that's the red curve, behaves the same as the actual function in the area, right here, I'm circling it, in the area where we are indeterminate. If you notice, the derivative and the function don't behave the same over here, and they certainly don't behave the same asymptotically, okay? But in the area where we care about, where we're trying to evaluate the limit, they behave the same because of that indeterminate form. Okay, and then you evaluate. So this is I call this a feedback loop. Okay, this last example, we evaluated and we got 8/7, and we stopped because we got a finite value, right? When you evaluate a limit and get a finite value, you can stop. If we would have gotten 0 over 0 again, we would have still been indeterminate. We would have gone back to this expression and differentiated it again. Okay, we're going to try one of those too. So that's why I call this a feedback loop. You're going to do L'Hopital's, you're going to evaluate it, and if you get a finite answer, you're done. If you get 0 over 0 or infinity over infinity again, you're going to come back up here and do L'Hopital's. Okay, and so L'Hopital's is something that can be applied multiple times, and they will definitely expect you to do that. Okay, so let's use let's do that. Let's use L'Hopital's multiple times. So first thing I'm going to do is plug in 0 because I have x as x approaching 0. So excuse me, I got 0 squared in the numerator. I've got e to the 0 minus 0 minus 1 in the denominator. That's 0 over 0. You don't even need to say 0 over 0, okay, because remember, we don't need to simplify algebraic forms. The grader will look at that and say, oh yeah, that's 0 over 0. All you need to do is verbalize, or in written form, indeterminate form. So this is telling the grader, hey, I'm going to use L'Hopital's and I know it's appropriate too. Okay. So notice, this is a subtlety, but it's an important one. I'm not using the equal sign anymore. I'm using an arrow because I'm going to differentiate. And when I differentiate, I'm not going to get an equivalent statement, but I'm going to get a statement that does the same thing at 0. So I can't use an equal sign. So I use an arrow. And I don't use a single arrow because I'm not approaching something. I use this double arrow. Sometimes you see it in chemistry, I think. Okay. Anyway, I call it a subtlety. It's actually kind of important. So I'm going to differentiate the top, right? Derivative of x squared is 2x. I'm going to differentiate the bottom. Derivative of e to the x is e to the x. Derivative of minus x is minus 1. Derivative of minus 1 is 0, so I didn't write anything. I'm going to plug in 0. But 2 times 0 is 0. And e to the 0 minus 1 is 0, right? Because e to the 0 is 1. Now, I'm not going to say 0 over 0 because, again, I don't have to simplify algebraic expressions, but I am going to state again that I have an indeterminate form. It's telling the grader that you're going to do L'Hopital's again, and it's appropriate to do so. So another double arrow, not an equal sign, because we're going to differentiate and we're not going to get an equivalent expression. We're just going to get another expression that's going to do the same thing as 0. Take the limit as x approaches 0. Take the derivative of the top, which is 2. Now I know I'm home free because that can never be 0. Take the derivative of the bottom, that's e to the x. Evaluate it. 2 over e to the 0. What is e to the 0? It's 1. So this limit is 2. And now I got a finite value, so I don't differentiate again, right? And so that is my limit. So that's how you use L'Hopital's multiple times. Okay, so let's talk about a graphical explanation of what's going on here, okay? So we started out with x squared over the quantity e to the x minus 1. That's this function here. And it's indeterminate, which means we have a hole at x equals 0. Okay, and then we differentiated it. We got 2x over the quantity e to the x minus 1. And that looks like this, right? It's not equivalent, but it does the same thing at 0. Right? That's the whole idea of L'Hopital's. G, function g, which is you're taking the derivative of the top and the derivative of the bottom and making a new rational function. It's not the same thing as f, right? But it does the same thing at that indeterminate location. But it itself is still indeterminate, right? It itself is still indeterminate. So I'm going to differentiate it again, and I get 2 over e to the x. Okay? And 2 over e to the x no longer has the hole at 2. It's been closed up because we no longer have 0 over 0. And now we can evaluate the limit using algebraic terms. Now let me just back up here for a second. You know, way back in the Unit 1 days, right? We might have given you this function, but we might have given you a graph, and we might have said, hey, what's the limit as x equals to 0, right? And we can see the left-hand limit and the right-hand limit both go to 2. We can evaluate that without having a value there. So we could have always evaluated this graphically. We just now can evaluate this analytically, right, using our algebraic and calculus tools. Okay, let's take it too far. I'm going to differentiate 2 over e to the x one more time. I'm going to take it too far, and I get this. And 0 over e to the x is 0, right? It's this purple line down here. Notice because I went too far, I differentiated something that's not indeterminate. I don't have the same thing happening at x equals 0. Okay, so so don't take it too far. You know, once you get that, don't just keep differentiating and differentiating and differentiating. You have to go back and check and verify you still have that indeterminate form after each differentiation step. Okay, so wow, I'm not quite sure why that's there. I think I have some animation that's out of order. So let me pause the video and fix that. Okay. I am back. Okay, so this is part of the activity for class period. I just want to go through one question just to kind of set the stage as to the expectations for L'Hopital's. So L'Hopital's, and I know I mentioned this in earlier videos. L'Hopital's, not the L'Hopital's things, but the idea of sneaking in the chain rule. And L'Hopital's is another really excellent way to sneak in the chain rule. So you have to be vigilant about looking for that. Everything's going to be a function inside of a function now. We're pretty much going to use the chain rule in almost every question. Okay, so we got to really be vigilant about looking for that composite situation. Okay, so I know you got some topic questions, but you also have this activity. So the activity is, what is the first derivative of a cow? It says find the following limits to match the questions with the answer. Place a letter in the space. Not every question that you're being asked in this puzzle are indeterminate limits. So there might be some that you can evaluate just by direct substitution. Okay, so like I mentioned a second ago, L'Hopital's is another really good place for chain rule to hide. So we're going to look at 7 and 9. So let's look at number 7. So where's the chain rule hiding? Take a second, look at that, right? We see our brackets. It's right here. We get a cosine function and we have a linear function in here. So when I see this, I'm thinking this. Okay, this pi over 2 is really a coefficient for x. Okay, so we look at this, we plug in 1, cosine of pi over 2 is 0, 1 minus 1 is 0. So we know we have an indeterminate form. So let's go ahead and differentiate. Okay, so derivative of cosine, the outside derivative is minus sine of what? This stuff inside, minus sine of pi over 2x. And then the derivative of the inside is pi over 2, right? So this is just a linear function, like 3x, the derivative will be 3. 7x, the derivative will be 7. Negative 34x, the derivative will be negative 34. Pi over 2x, the derivative is pi over 2. Okay, so there's our hiding chain rule. And then let's take the derivative of the bottom, which is just 1. We know we're out of the woods because the bottom can never be 0. We don't have to do L'Hopital's again. We can plug in 1 for x. 1 times pi over 2 is just pi over 2. Sine of pi over 2, it's the top of the circle. That's 1, right? Sine is the y coordinate. So 1 times negative 1 is negative 1 times pi over 2 is negative pi over 2. And when we look down at the bottom of the puzzle, negative pi over 2 is letter E. So we should be putting an E there. Okay, some more. Let me pause the video, get my animation. Okay, let's take a look at number 9. So, still looking for that hiding place for the chain rule. Okay, so where's the chain rule hiding here? So we can see that we have a sine, and we don't have brackets here, but we should think of it as brackets, right? We have sine times the quantity 6x. So we have a sine, a trig function, and then another linear function, 6x. We plug in 0, we get sine of 0 over sine of 0. We know sine of 0 is 0, so this is 0 over 0. So we know that L'Hopital's is an appropriate course of action since we have an indeterminate form. So we take the limit as x approaches 0, and we take the derivative of the top. So derivative of sine is cosine. Cosine of what? Cosine of 6x. And then the derivative of the inside is 6. And then we do the same for the bottom. Derivative of sine is cosine. It's cosine of 4x. And then the derivative of the inside is 4. So there's the chain rule that's hidden in each one of those. Now we plug in 0. So we get cosine of 0 times 6, which is 1 times 6. We get cosine of 0 on the bottom times 4, which is 1 times 4. So we have a limit of 6 over 4, which is letter B. And then we can put letter B into the puzzle. Okay, so when we get back into the classroom, we'll go over the takeaways and do those type of questions and finish up the puzzle.